Good day, students. Today I will be discussing binary vapor power Rankine cycle and plant. To illustrate this power cycle, let us have this example. The binary vapor cycle operates on mercury and steam. Saturated mercury vapor at 4.5 bar is supplied to the mercury turbine, from which it exhausts at 0.04 bar. The mercury condenser generates steam at 15 bar and is superheated to a temperature of 300 degrees Celsius in a superheater located in the mercury boiler. It is then expanded in the steam turbine to 0.04 bar. Also, 50,000 kg per hour of steam flows through the steam turbine. The isentropic efficiencies of the mercury and steam turbines are 0.85 and 0.87 respectively. The properties of saturated mercury are given in this table, and we are going to determine the quantities found from letters A to I. So these are the key words or given in this problem. So this is a binary vapor cycle. If you remember binary vapor cycle, it's like a combination of two Rankine cycle by which we have the topping cycle and the bottom cycle. The topping cycle is the mercury because of its properties, and the bottom cycle consists of a steam cycle. So in the topping cycle, which is the Mercury cycle, saturated mercury vapor at 4.5 bar is supplied to the mercury turbine, and then it exhausts that mercury turbine at 0.04 bar. So it means that the topping cycle operates at a boiler pressure of 4.5 bar, and its condenser pressure at the heat exchanger is 0.04 bar. This mercury condenser at 0.04 bar generates steam at 15 bar. So it means that since this mercury condenser serves as the boiler of the steam cycle or the bottom cycle, it is able to produce 15 bar of steam at a superheated temperature of 300 degrees Celsius. So since it is a heat exchanger, it is necessary to superheat the steam in the superheater located in the mercury boiler so that it will reach 300 degrees Celsius superheated. Then this steam is expanded in the steam turbine to 0.04 bar. It is also given that the steam flow rate in the bottom cycle or the steam cycle is 50,000 kg per hour, and we are given with the isentropic efficiencies of the mercury and the steam turbines respectively. So it means that we are solving this in the actual scenario. And then we're going to solve these unknown values here. So this is the equivalent schematic diagram. So we have the topping cycle consists of the Mercury cycle, process 1, 2, 3, and 4. And we also have the bottom cycle consists of the steam cycle, process 5, 6, 7, 8. So if we look at the two cycles, they are connected by the heat exchanger. So this heat exchanger serves as the condenser of the Mercury cycle and serves as the boiler of the steam cycle. Since this heat exchanger is not enough to superheat the steam in the steam cycle, that's why we use a superheater. This superheater actually is connected to the mercury boiler, but it was not shown here for simplicity. But the purpose is just to superheat the steam that we can produce from this heat exchanger. So if you're going to look also, since there's no mixing in the heat exchanger, the mercury cycle and the steam cycle has separate loops, and thus they have separate mass flow rate for the mercury cycle and separate another flow rate for the steam cycle, which is given in the problem. Also, based on the problem, the boiler pressure is 4.5 bar and the condenser pressure of the mercury cycle is 0.04 bar. That's why the topping cycle, as you can see here in the TS diagram, is composed of 4.5 bar and 0.04 bar. It's also given in the problem that this turbine here for the mercury has isentropic efficiencies of 0.85. That's why there's a deviation from the isentropic process 3 to 4. And the bottom cycle consists of process 5, 6, 7, 8. It consists of the steam cycle operating at 15 bar condenser pressure and 15 bar pressure for the for this mercury condenser, which serves also as the boiler of this steam cycle. That's why we have 15 bar upper pressure and 0.04 bar lower pressure for the steam cycle. And similarly, we have isentropic efficiencies for the steam turbine 0.87. That's why we obtain a deviation also from the cycle. So what we are looking for is to solve for the enthalpies for all the points 1, 2, 3, 4, 5, 6, 7, 8, and also to solve for the enthalpies 4A and 8A. So we can simply analyze this by solving each of these cycles separately. So first, we're going to find the enthalpies in the Mercury cycle, the tapping cycle. So for the Mercury cycle, we are given with these properties here based on this table. So the properties are given because of the fact that it's difficult also to find the table for the properties of Mercury. So using the table, we know that H1 is saturated, a saturated mercury liquid. So that's why we will use H1 is equals to HF at 0.04 bar. So at 0.04 bar in our table, we're going to look at HF. The value is 29.98. That's why we have here 29.98 kilojoules per kilogram. Then we have process 1 to 2. This is a pumping process, a pumping for the mercury. So in some problems, the pumping is being negligible because the value is actually very small. But for this problem, since we have the means to get that value, we're going to solve it by using this formula. H2 is equals to H1 plus the pumping work for the mercury cycle. So we already have H1, so our problem is the pump work for the mercury cycle, but we can solve that using this alternative formula by multiplying the specific volume at point 1 to the pressure difference across the pump. So that's why we have H1 is 29.98 and the specific volume at point 1 is the VF at 0.04. That's why the VF at 0.04 is 76.5 times 10 to negative 6 based on the table, and we multiply it with the pressure difference across the pump. So we just convert this bar to kPe so that the result will be kilojoules per kilogram. So this is already the converted values of bar to kPe. So that our H2 is 30.014 kilojoules per kilogram. So if you're going to examine the difference of enthalpies across the pump, it's just very small. That's why sometimes the value is being neglected in some calculations. At H3, this is already a saturated vapor at point 3 based on the problem. It's not superheated also. That's why we can use the Hg at 4.5 bar, and that is 355.98. So that's why we have here H3 is equals to 355.98 kilojoules per kilogram. For point 4, we're going to find first the value of the quality at point 4. We can solve that by using this relationship between the entropies. So we have S4 minus S1 over Sg minus Hf. This S4 is the value of Sg at point 4, and S1 is the S4 is the value of the entropy at point 4. S1 is the value of entropy at point 1, and then we have Sg minus Sf is the difference between the entropy of the 0.04 bar. So if we're going to substitute the value, S4 is just equals to S3 because this is isentropic process, and S3 is the Sg at 4.5 bar. That's why at 4.5 bar the Sg is equals to 0.5397. That's why we have here 0.5397. S1 is the value of Sf at 0.04 bar. That's why we have Sf at 0.04 bar is 0.0808. They are the same with Sf. That's why we have 0.0808 also here. And for Sg, that is the value of Sg at 0.04 bar. That's why we have 6925. So the value of quality is E0.7502. So the quality is 75.02% at the outlet of this mercury cycle. And then we can now solve the value of H4 by substituting with the value in the relationship HF plus X multiplied by the latent heat of vaporization, Hg minus Hf. So substituting the value, also from the table, we have Hg for 0.04 bar is 329.85 and the Hf is 29.98. That's why we have H4 is 254.94 kilojoules per kilogram. Since there is a deviation in this cycle, we need to obtain the value of 4A. We can obtain that by using the isentropic efficiency relationship, which is H3 minus H4A divided by H3 minus H4. So we're going to substitute the value. We know that the isentropic efficiency of the Mercury turbine is 0.85 based on the problem. And we can solve now for H4A, and that is 270.096 kilojoules per kilogram. So we obtained the enthalpies H1, H2, H3, and H4A for the Mercury cycle. For the steam cycle, we can use the software since the water is available in that. So we simply use the values that we can tabulate. So the steam flow rate is also given. It's 50,000 kilogram per hour. So at 0.5, this is a saturated liquid. It's just like the simple Rankine cycle actually. So you just plug in the value in the table, in the software. You can get all of the unknown quantities. And then we have process 5 to 6 is isentropic process. And then we can also get the two unknown values. 0.7 is a superheated vapor at 15 bar and 300 degrees Celsius as given here. So we can also obtain the value. And then finally, process 7 to 8 is isentropic process. We just substitute that and we can finally get the value of temperature, the quality, and the enthalpy. You can find here that the quality is 80.73%. So that's actually below the requirement, which is 90%. So there's also a need to improve this cycle. Since this is an isentropic turbine, we need to get the value of H8A. So using the relationship H7 minus H8A over H7 minus H8, we know that the isentropic efficiency of the turbine of the steam is 0.87. So we can also get the value of H8A, and that is 2,208.307 kilojoules per kilogram. You can also find here that because of that deviation, there's an increase in the quality of the liquid exiting the turbine. You can actually solve also the actual value by plugging in 2,208.307 and the pressure of 0.04 in the software. Try to put it. Let us see if it meets the requirement of 90%. So these are the summaries of enthalpies based on our previous calculation. So now that we have the enthalpies, we can solve the first unknown, which is the mass flow rate through the Mercury turbine in kilogram per hour. Using energy balance in the heat exchanger, energy in is equals to energy out. We know that the energy entering are 0.4 and 0.6 and leaving are 0.1 and 0.7. So that's why we have this relationship. The mass flow rate of the heat exchanger, M1, is just equals to M4 because this is just one loop here for the Mercury cycle, and that is equals to the mass flow rate of the Mercury, which is the unknown in this problem. And then we have M6 is just equals to M7 because this is the equal loop. So that's why we have this relationship equals to MS, or the mass flow rate of the steam. Substituting that in the equation, we can get this one and just rearrange that and get the value, the ratio, and solve for the mass flow rate of the Mercury in the Mercury cycle. So the mass flow rate through the Mercury turbine is can be solved using this relationship. So we just plug in the value from this summary of enthalpies here. We can now get the value of the mass flow rate through the Mercury turbine. So the value is approximately 607.63 kilogram, or we have 607.63 kilogram steam flows through the Mercury cycle per hour. So if you're going to examine it, it's actually an enormous amount of mercury. That is actually one of the disadvantage of this kind of power plant, because it uses an enormous amount of mercury, which needs very careful handling, and we need to avoid also the leakage of this, as this is dangerous to our environment and also to people working nearby the power plant. So this is actually one of the disadvantage of this kind of design. Now let's proceed to the total pump work input required, so that we can find in the problem that there are two pumps. We have the mercury pump and then we have the steam pump. So we can actually combine them so that we can have this relationship here. We just simply multiply the flow rates of the pump to the change of enthalpies across the pumps. So plugging in the values that we solved previously and also the enthalpies found in this table, we can get the total pump work input for the mercury, that is 5.733 kilowatt, and for the steam cycle, that is 20.833 kilowatt. So the total pump work is 26.566 kilowatt. You can find here that the plant will need 26.57 kilowatt of power to run, and out of that, 5.733 kilowatt is for the mercury pump and 20.83 is for the steam pump. You can find that we can actually neglect the value of the mercury pump sometimes because it's actually very small. For the total turbine work, turbine power output in megawatt, we have two turbines. We have the mercury turbine and we have the steam turbine. In the same way, we can also combine the two value to get the total turbine power output. And then substituting the value, we can get the turbine work output for the Mercury cycle and also the turbine work output for the steam cycle. You can see here that the Mercury cycle produces more as compared to the steam cycle. That is actually the reason why we use the Mercury cycle as the topping cycle to take advantage of its properties and get a greater amount of power output. So combining the two, we can get the total turbine power output, which is 26.008 megawatts. The back work ratio can then be computed by using this relationship for the back work ratio, which is substitute the value in megawatts for the pump and the turbine works. So the back work ratio is 1.02%. For the net power output, we just simply find the difference between the work of the turbine and the work of the pump. So we can get 25.742 megawatts. So be careful to convert the value for the pump work to megawatts so that we can have the same units. So the plant power capacity is 25.74 megawatts. For the total heat input in the mercury boiler, so we are referring to the mercury boiler. So take note that in this cycle, there's only one heat input, and that is the heat input from this boiler. There's no heat input in the heat exchanger because what happens here is just heat exchange between this process 4 to 1 and the process 6 to 7. So the only heat input is the heat input from the boiler, and the superheater is also the heat that we use to superheat the steam is actually also from the mercury boiler. That's why we just solve for this portion. And that is simply the mass flow rate of the mercury multiplied by the change of enthalpy across the mercury boiler. Substituting the value, we can get the total heat input in kilowatt and convert it also to megawatt. So the total rate of heat addition from the mercury boiler is 54.97 megawatts. On the other hand, the total heat rejection is in the condenser of the steam cycle, and that is simply mass of the steam multiplied by H8A minus H5, or the enthalpy difference across the condenser. So the heat rejected is 28.95 kilowatt, or simply 28.99 megawatts. So you can see that out of the power, the heat that we produce in the boiler, 28.99 megawatts is wasted. So the thermal efficiency can already be computed using the formula work net over QA. Substituting the value, we can get the thermal efficiency as 0.4683 or 46.83%. So it means that 46.83% of energy from the mercury boiler is converted to useful power output. So in actual power plant, 46.83% efficiency is actually a very good efficiency already. Heat rate can also be computed by using the formula. So the heat rate is 7,286 BTU per kilowatt hour. So that is how you analyze binary vapor power Rankine cycle. So it's like solving for Rankine cycle, for the Mercury cycle, and also for the steam cycle. So I hope that you understand, and if you have a question, feel free to comment down below or send your message in our channel.